Alright, so continuing on, what we've done so far, just a synopsis in this chapter, because we're going to add one other thing to it. I'm trying to wrap up. We started with figuring out central tendency, where data tends to tendency. Ooh, I've got a spelling issue. Central tendency. And we use that using mean, median, and mode. And this described where the middle of the data is. Or where the data clumps, where most of the data is, where the data is clumping. And that helped us, explain and sort out differences between different data sets. The mean focused on the center of the values of our data. The median focused on the center of the actual number of pieces of data. And the mode looked for where the most reoccurring piece of data was. And we found with the Corp A and Corp B example that we used that you could have the same mean, median, and mode, but be completely different because the variance in your data, which the standard deviation is our main guide, or how much your data varies from the mean. The average distance from the mean, I think, is a good way of kind of talking about the standard deviation conceptually. And we could have the spread. Well, now we kind of want to talk about position in our data. And if we notice in the empirical rule, we could talk about what percent of the data is in a certain part, how much of our data is positioned at certain numbers. So what we kind of want to do is we want to find ways of measuring our data. And so we're going to talk about things called fractiles, which are numbers that break our data into equal parts. And equal parts in the number of data. We actually learned the first fractile, which was the median. If I have all my data together and I find the median, I have 50% of my data on one side of the median and 50% on the other, because it divided the data in half. It's the middle of the actual data point. And fractiles are a way of doing that. Now I'm only going to examine one type of fractile, and that's going to be what's called quartiles, where we divide our data into 4 equal parts. Or quarters, right? We quarter our data. And so I'm going to do it, and then I'm going to label out the different parts on it. This really relies on the concept of how we found our median before. And so the first thing we really need to do is we need to organize our data from lowest to highest. Now I'm going to pre-sort the data that's the example in slide 6, but we're going to organize it in order. And so this is the 15 largest urban areas in the US and how much gallons per year of fuel is wasted in traffic. Commuter waste of fuel in gallons per commuter. Oops. This is a little bit easier on a blackboard in person. I'm going to have to redo some of this here. Let's see how far back I can get here. Up here. I just need to make it a little tighter, so I need the space. 22, 23, 24. I have 3 25s. Sorry, as I put my data down, there's an awkward silence online. but I will write, we will live with that awkward silence. And so I should have 15 pieces of data, so I double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And so to find quartiles, I start by finding the median. And so I have to count out equal things on either side. So I'm just going to alternate my way through until I get to the middle piece of data. See how I'm cutting off each end? This works a little bit easier on a blackboard. I can put my hands on both sides. What I'm doing is I'm using the process we use to find the median, and there it is. There's the median. I'm also going to call this something else now. This marks the boundary of my second quartile. And so we're going to say it's quartile 2 with this little symbol. Now what I've done is I've divided my data into 2 equal parts. Well, if I want to quarter this, I'll find the median on each part. So finding quartiles is you find the median, and then you find the median on the parts you've made. So I'll do the same thing here. I'll do my up and down trick. Work my way towards the center, finding the median. So that, whoops, this one should be down, right? Get off that endpoint, get off that endpoint. And that's the median of the first 50%. And so that divides that, and that's going to be my quartile 1. That's my first quartile, and that's my second quartile. Now I'm going to do the same thing on my other side of the data here. So I go upstairs. All right, I'm finding my median 3 times. And for here it's 30, which is going to be quartile 3. And what this does is this makes some points for my data. I have the min point, which was 11. I have quartile 1, which is at 23. I have quartile 2, which was the median at 25. Quartile 3 at 30. And quartile 4 at 35. Now if we look at our data, the range, which is the max minus min, which is 35 minus 11, or 24. And so this whole data ranges over 24 spaces. Now let's look at what we can graphically do with this. So we notice that 11 to 20, there's a big gap of 9, but in here, there's big chunks of data. And so if each of these chunks is 25%, we're going to look at the inner, or the interquartile, which is from quartile 3 and quartile 1. In between these two, if each of these is 25%, this is the middle half of my data. And so we'll talk about the interquartile range, which gets abbreviated IQR, and it's Q3 minus Q1. In this case, 30 minus 23, which is 13. So let's see here. As I make sure I copied my data down correctly, I go over my notes here. So you'll hear my notes rustling periodically. So that's where I'm at. Should I have my numbers right here? So 30 and 23. Oh, 30 and 23 doesn't make 13. This makes 7. I was thinking of 43 and 30. Don't know why. All right. So there's our interquartile range. Did you ever do that? You knew a number was wrong and you needed to double check. So I just flipped through my notes. I didn't even have it written down, but it helped jog my memory. And double checking our work's a good thing to do. And so my whole data runs over a range of 24, but the middle 50% is cramped within 7 numbers. And so we're going to make a way of representing this. This is called a box and whisker plot. And what I do is I make a number line that spaces out my data evenly. So I'm going to start on 11, make my number line here. Start on 11. That's 11. And then I need even markers. And there's 35. And so what I need to find now is I'm going to mark each of these points. So I'll start by marking quartile 1, which is at 23. So there's 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Yep, 23. And so we'll say quartile 1. The boundary at quartile 1 is there. That's 23. It's 24, 25. Well, there's my median. So quartile 2 is there. There's 30, which is quartile 3. And what we'll do is we'll have our median marked and we'll draw a box from quartile 1 to quartile 3. And then we'll draw whiskers from those boundaries of the quartiles all the way out to my min and max. And that's why it's a box and whisker. And this box here is 50% of our data. And so we can see 50% of our data is clumping really, really close to here, while 25% of the data is spread out here and 25 is here. I can actually, when seeing a box and whisker plot, kind of see that there's probably a histogram like this in the background somewhere. Right? Things are clumping here in this middle, right? Probably around the median, so probably more like this, and coming down. But a box and whisker plot shows it to us nice and quickly, and it shows us where 50% of our data is in the box, and then where the other 50% is in the whiskers. Well, position is a very important thing for this. Finding position helps us get our way around data, and it helps us actually find a way of talking about the uniqueness of individual values. And so the last thing we're going to define in this chapter is called the Z-score, the Z-score for Americans, Z-score. And the Z-score is defined as my X value minus my mean divided by the standard deviation. I'm going to put little subscripts here because this works for each piece of data. And of course, hey, here we're talking about a population. Over here, we're talking about a sample. Right? Different variables, but the same process. And so this equation gets used as a way of talking about the uniqueness. And I want to use the Z-score to kind of talk about the uniqueness of an individual piece of data. So we'll draw my normal curve. That was a line. What I should really do is graph one out and just copy and paste it. But the drawing it is something that I think emphasizes its form. It's not a fry guy, it's a normal curve. It's not a fry guy, it's a normal curve. Right? Just sketching on my pad here. Let's see if I can get, yeah, that slides. I don't know, my left sides are always weird. All right. Well, and we have our mean here, and this is going to be the same for any distribution that approaches normal. And so these numbers can just change for what we're looking at, but the distribution is. So we have a highway that has a mean speed that has been measured to be 56 miles per hour. And it has a standard deviation of 4 miles per hour. That means here and here, from 60 miles per hour to 52 miles per hour, is 68% of my data. But I can have 3 different pieces of data. I can pick 3 pieces of data out. Randomly, I'll grab data piece number 1, which is 62 miles per hour. Well, what does that mean? Well, let's use the z-score to work it out for us. So I'll do the z-score for data number 1, and I'll use the formula. So it's my xi, which is 62, minus my mean, which is 56 miles per hour. I'm going to divide it by 4 miles per hour. Now what you should note is I have miles per hour as my unit upstairs and miles per hour as my unit downstairs. That means the unit cancels out, and z-scores are pure numbers. So we can use them to compare, and they talk about measuring things in the terms of standard deviation. So 62 minus 56 is 6 divided by 4, which is 1.5. That means this piece of data, x1, with a z-score of 1.5, sits here. There's z1 equal 1.5. That means this particular car that we randomly picked is not within our 68% in the middle. And it has a position in this distribution relative to the mean. All right, let's look at another car. We'll pick out x2. I'll do that in bright yellow, red. And so we have another car that we ran, or yellow. I'll randomly pick out. It's going 47 miles per hour. And so we'll calculate its z-score for data 2. And so 47 minus 56 divided by 4. And so what do we get? We get negative 9 over 4, or negative 2.25. Now again, this has no unit, so it's measuring over here. And there is a z number 2 of negative 2.25. We have a positional value, and we know how this data compares to where the bulk of the stuff is and where other things compare. Well, let's look at the usefulness of this. And let's take another normal curve. And we're going to use this for 2 types of data. And so if I said to you, let me draw my normal curve first. If I said to you that there was a man who was 6 feet tall, 6 foot tall man, that's not rare. But if I said there was a 6 foot tall woman, we would think that's rare. So what does it mean to be rare as an event from observed data? Well, let's use our standard distribution. So first off, the average height of men in inches is 69.9, with a standard deviation of 3.0 inches. The average height of women is 64.3 inches, with a standard deviation of 2.6 inches. So if I have a man, I'll make this x1. Now these are 2 separate distributions. There's 2 different bell curves, but we're going to use the z-score to compare them, because the bell curve is the same shape, the same distribution, no matter what my mu or standard deviation is. It has the same shape. The tighter the standard deviation, the narrower it is, the longer, the bigger. But your positional value, or your z-score, relative to your data, can help find your value. So let's find your position. So let's look at the Z1 for men. So 69.9 minus, I'm sorry, I'm talking about a 6 foot tall. All right, so a 6 foot tall man is 72 inches. My bad. Had to convert that to inches there. So 72 minus 69.9 over the standard deviation of 3. Well, 72 minus 69.9 is 2.1 divided by 3, which is 0.7. So a man that is 6 feet tall has a Z of 0.7. And it's within that 68%, which is why we don't think it's rare. We don't think a 6 foot tall man is exceedingly tall. But we do the same calculation on the distribution for women. Again, different distribution, but we're using the z-score to talk about the position. And so we get 72 minus 64.3 over 2.6. Running to my calculator, I get 2.997 or approximately 3. And so for a woman who is 6 feet tall, they have a z-score of 3. And it's within here in the distribution, which is more rare. It's very far away from 68%. And so what we can generally say is that we have usual scores within the usuals within 1 standard deviation. Unusual scores are within 3, and 3 and above, or starting at 3, is very unusual or rare. And so now the standard deviation and using it to make z-scores have us a way of telling how rare one piece of data is within our distribution. And so it gives us a comparison metric for individual pieces of data, no matter what their distribution. And so we can talk about the rarity of this man's height, and we can compare that to the rarity of this woman's height. And your brains actually already do this. When you think of someone who's tall, your brain kind of has a bell curve in the background. We have words that go around that, and we do these statistics internally.